Okay, we're live for YouTube now. So to review, since it's always good to kind of refresh after the weekend, we were just talking about stacks and queues, primarily stacks, since I explained to you that stack is a last in first out method, meaning that the last item that's put in is the first one that gets taken out. A stack is not particularly a specific implementation of a data structure, but it's sort of a concept that you can implement in different ways. So you can implement a stack with an array or a vector. In fact, the vectors push back and like pop or whatever that's called are literally a stack. They work for a stack. But yeah, so a vector, an array, or a linked list, and obviously with a linked list you have things like singly and doubly linked list. They're all ways of implementing a stack. So whereas a linked list is actually like a specific way of implementing something in C++, or well, other languages too, a stack is not that. A stack is more like higher level, in the sense that like you're not talking about a specific way of implementing it. You're only talking about what it needs to store, the order in what it stores it as, and what are the functions that you need. So it's like if you think of two days when you're creating a class and you're trying to see like what's the data and the operations on that data that you're trying to work with, the abstract data type. That's what you kind of decide in your head when you're implementing a stack, and then you don't worry about, or I mean, when you're designing a stack, and you don't worry about like how that is actually going to be put into place. Now, of course, in the assignments you have to do that, and you do, and that's different. But like I'm saying in general, okay? And so the two operations that you have with a stack are your push and pop. Your push throw something in the stack, and pop takes something out. And we also kind of did a quick comparison of the different ways of implementing a stack between a linked list and an array, and seeing what are the pros and cons. And we basically concluded that the linked list implementation of a stack is the quickest in both terms of space and time. And that is because you are able to just keep inserting as long as you have memory in a linked list without having to search around or resize and whatnot. And that's the big disadvantage with an array implementation of a stack, that you are limited by the size that you allocate. And whenever you need to resize a stack, that is going to take you time. It's going to take you O of n time. And so that's going to slow down your insertion time. And technically for the pop, you could leave it really big and then not like resize it whenever you take something out. But the disadvantage of doing that is that you're going to always have a little bit more space than you need if to be able to not always be stuck with that O of n insertion time, because you have to have a little space extra to either insert some things in the future, or if you take some things out, there's no point in resizing because you might put something in later. So, to kind of achieve O of 1, which will not always be the case because there will be a time when you will have to resize, but to achieve it the most of the time, you are going to have a little extra. You are going to allocate, when you resize your stack, you're going to like double the size, or you're going to add like 20 extra spots, right? So that way you're not resizing like every single time, but every 20. And that kind of helps out. But again, because you do have to resize, we say O of n. And the disadvantage, of course, when you think about space analysis, is of course that you have to have that extra space ready to go, which you're not technically using. So it's I don't want to say wasteful, but it uses more space. Okay? So does that mean you should always implement a stack as a linked list? If you're talking about like a pure stack that's only going to have what I just told you, then, I would say, okay, sure, I would go with the linked list approach. However, even though I tell you like, okay, you should have a push and a pop, there's always going to be, like rules are meant to be broken kind of thing. There's always going to be one person who's going to be like, yeah, but what if I want to see what's at the bottom of the stack? Well, you can just write a function that looks. I mean, like, just because you say you're not supposed to do something doesn't mean like if the project calls upon you requiring to see that, then it's just as easy as looking for it, right? It's not like some sacrilege you're breaking by looking at the bottom of a stack and editing something there, or even removing it. You are going to have to write some extra code to get that working, and be careful about it and be aware that such thing can happen, but you can do it. And if you do that, then I would argue that maybe the array implementation may actually be more beneficial, because that allows you to quickly access any index that you want. Whereas the linked list, yeah, you can actually access the back of it, but with a tail pointer or something. But if you're trying to access the middle of it, that's going to take over in time. So also, I suppose if I don't know how realistic this is, but if you're trying to print out the stack, maybe printing out an array is a little bit quicker than printing out a linked list, especially if you have a multi-core computer that can actually do, or actually, I don't know if the multi-core will help, but the thing about the linked list is that as you print, you have to dereference to the next spot, right? And the dereferencing technically takes a little bit of time to go and pull that from main memory. And so when you get to like 219 and you're talking about like cache and branch prediction and all these things, technically, if you're going to pop out like 100 items from the stack at once, like really quickly, back to back, you can kind of, the operating system can predict that it can predict that you're doing that. After you do it like 20 times, it's gonna be like, okay, this person's just like removing nonsense from the stack. So it can like preload part of that stack into your cache memory, which is faster than your main memory, which is faster than your hard drive. So it can preload that into memory to be able to access it quicker, because it thinks you're going to do it. And if you don't, it's fine. It just preloaded it for nothing, but the time saved is going to be like on the order of 100 times faster. And so with an array, that's very easy to do, because you know exactly what the next spot in the array is at memory-wise. In main memory, an array may actually not be a contiguous block of memory. Like, that is what you see, but in memory, things might get a little bit different when you're loading things in cache and whatnot. But it still knows exactly where to look. So it can cache that in, and it can preload that. With the linked list, because of the way I told you that linked list allocation work, where like things get stored all over the place, it's a little bit trickier to do that. And so it might not be as efficient as that. So there's a lot more to look at this than what I'm telling you. Those kind of things are things that are more like in practice, how computers are implemented, and you'll learn in 19. Here we're just looking at the overarching sort of view, and that's why we're claiming these time complexities. But of course, in practice, things get a little bit different. So don't just go out and argue with everybody. Oh, my professor said the linked list stack is the best one. I will never do anything else, because there are exceptions to the rule, and theory versus practice is not the same thing. Okay? So just a little spiel about that. Have fun when you take 219. I do have on YouTube, self-plug, the entire 219 I did over the summer, like last summer, not this summer. So, if you're bored, I guess you can watch those and, prepare for 219. But yeah, okay. So that's a stack. Let's talk about queues. So whereas a stack is a last in, first out, as a queue is going to be a first in, first out. And again, that is basically how you go and stand in the line, whether you're at a supermarket, grocery store, or you're at Disneyland, or pretty much anything. I mean, if you, like anytime that you think about organizing somebody to wait for something, they are hopefully doing it in the queue, unless you're like in a really badly organized place and like they do a stack or something, because that would be very like messed up. Or of course, if people cut the line and they violate the queue, right? But basically, in fact, British people use queue instead of line. So there you go. Just think British when you're thinking about what queue is. And so when it comes to a queue, there are different ways of implementing it. There's the linked list way, and then there's the the array way. And so just to be clear, when you're doing a stack implementation or a linked list implementation of a stack, let me just make sure that we're all on the same page of how you actually would do that. Now, I'm not going to write code because that would take too long, but at least I'm going to draw a picture of what you would be doing. So and the reason why is because this will kind of go into how you do a queue with a linked list. So when you have something like this as a linked list, you have your head and tail pointer, right? And then actually I'm going to write the words head and tail here because I'm going to use different terms in a minute, okay? And so when you're inserting something into a stack, the easiest thing to do, I mean, here's the thing. Let me show you the wrong way to do it first. You might think, okay, you know, head and tail. Head is like the beginning of something and tail is kind of the end. That's how we sort of think about it. So you might be tempted to add, or when you push something into a stack, to put it at the tail end. So you just copy the tail pointer and then assign that to your new node and you call it a day. That'll work for your insertions, but when it comes to removal, you know, because you update this tail pointer now to basically, you know, point to the last item. So before, actually it was pointing here. I might have misled you how I wrote that. Before, you know, this was pointing to null. Okay, and what I do is I say, okay, tail next gets whatever this node is. Okay, like that. And that will go ahead and put this in the tail, like this. And then I can just update tail to be equal to that value, that temp or whatever it is, okay? So that'll work fine for insertion. The problem with doing that is that when it comes time to pop that item, you know, sure, you can see what it is because you can just see what temp is pointing. So like temp data or whatever is pointing here, so that's cool. Sorry, not temp, tail data. And then you can even delete it by saying temp delete, which deallocates it. But you're not able to easily remove it or to get rid of this pointer here and set it to null and then move the tail back once. So you have to traverse the entire linked list to do that. Of course, that defeats the whole purpose of doing the linked list implementation of a stack. So that's why you wouldn't do that. Now, of course, if this is a double linked list, you don't run into that problem. However, I would say that using a double linked list is overkill because you can easily do this with a single linked list by, instead of inserting at the end, inserting at the beginning. So I'm going to just go ahead and rename in this. In fact, you don't even need this tail pointer. You can throw that away. However, instead of calling this head, a nice name for this is called top. When people say top of the stack, there's some terminology for you. What they're saying is that the first item that's going to come out next time they pop. Okay, that's what top means. So the arrows here look misleading because the top is like the back arrow, you know, and the front of the arrows is all the way to the right. It's misleading in that regards, but this is the best way to implement it because now, if I want to throw something into my stack, so if I want to push something, I have my little node here. I'm going to call this temp. And what I do for this is I just take this value, some temp next or whatever I call it, which is this here, and copy the value of top to that. So temp next gets top, something like that. And by me doing that, what I basically achieve is to make this pointer point here, okay? And then all I gotta do is update the top to no longer point to what is now the second node, but to point to the first node. All I have to do is say tail, or sorry, no, top gets tail. Wrote that backwards. But yeah, top gets tail, okay? And what that does is it makes that point here, and we're good to go, okay? That's how you push. So again, push is good, but does pop work this time? Yeah, it does, because now if I want to get the value from when I pop it, I just look at top data, and then I can return that or print it out, whatever it is that I'm doing, I can access it. I can also deallocate top and go next to get the next one, but of course, that's that dangling pointer issue. So what you don't want to do again is say something like delete top and then make top equal to top next. Because again, that's a dangling pointer. So you got to make another temporary pointer in the meantime. So say something like temp gets, well, say node period temp, so make a new pointer and then assign that to say top next. And then delete top and then assign top to get to be basically that temp. Okay? By you doing that, you've just added one extra line of code, but you avoided dangling pointer. Okay? So yeah, that's all I'll say about that for insertion. Okay, so that's how you would do the insertion. Okay, so when it comes to a queue, in the queue, by the way, there's some terminologies that we want to talk about. So when you insert something into a queue, we call that enqueue, and when you remove something from a queue, we call that dequeue. And then instead of calling something head or tail or front or top, as it is the case with the stack, the beginning of the queue to the next item to come out of the queue is going to be called, surprise, surprise, the front, like front of the line. And then you can also, if you want, call the back of the queue or the last thing that was inserted, just back, okay? So again, some good terminology. The reason I'm telling you this terminology is not because I'm going to ask you like vocabulary words in the exam, but it's because I want you to be able to recognize when somebody talks to you and says like, hey, you know, insert this into the front of the queue, and then you're confused what that means. You know, you got to know that stuff. Otherwise, you look like an amateur if you're working. So you don't want to look like that, right? So yeah, okay. And these are really basic at this point, but yeah. So I'm pretty sure you would have guessed it if somebody said insert at the front of the queue, what that means. But you know, sometimes some of these terms might be tricky later on the semester. Okay, so yeah, okay. So let's go ahead and implement this with a linked list again. So that is a little bit tricky as well for the same reason. Now that you understand why we do the stack the way we do, hopefully it makes sense why we don't want to make the front of the queue here. So I'm going to say F for front and B for back. Because if I do that, again, if I remove something, so if I dequeue something from that, which means get rid of this, I have no easy way of moving this pointer back. So because of that issue, I'm going to go use the same exact approach I did on the stack, which is to make my front be here. And then make my back be here. So the arrows are a little bit misleading when you're drawing a linked list, but that's the best way. Because you only ever insert through the back of the queue. And so to insert is as easy as just saying back next. So I'm going to abbreviate the N for next. Back next gets whatever your new node is, temp, and then just update back to point to temp. So that's your insertion, so that's your NQ. And then for your DQ, I'll just abbreviate the DQ to DQ, is going to be just to, or sorry, to DQ is just, again, you know, access data, which I'll abbreviate with the D, you know, store that wherever you want, put it in a temporary variable, make an, if this is int, you know, make an int like T and then assign it, whatever it is you need to do with that data, copy it then, so you don't lose it. Because remember, the DQ process, you know, the stack and the queue are destructive in the sense that, like, when you remove something from a stack or a queue, you are both retrieving and deleting. So you got to make sure you know, because you want to deallocate before you exit the function, you want to store that somewhere temporarily, and then deallocate. So you don't, again, accessing a dangling pointer, and bad things can happen, especially if it's like from a function going back, and you don't want that. So anyways, yeah, so access the data that way, and once you're ready to deallocate, make again a temp pointer to avoid the dangling pointer issue, and just store F next there, and then go ahead and delete. Delete your F, and then I ran out of space, so let me scroll this down. Go ahead and update F to point to the second item, which is now the first item, by saying temp. Okay? So that is as trivial as it is to do this. Of course, you have to make sure you remember how to actually do linked lists in the first place, but you know, they're not bad. Okay? How do we feel about all this? I hope you're all very quiet today, so I hope that this is all obvious, because you all like saw stacks and queues in 202 maybe, so that's okay. All right. With the array implementation of a stack, I do want to talk about that one. That's kind of going to be the focus of today, because that's a little bit interesting and kind of cool. Kind of gets this round robin feel for it. So if you all try to implement a queue with an array, things get a little bit messy. You know, let's do the naive way first. You know, the naive way of implementing a stack, because it's always good to make mistakes because we can learn from that, right? So let's make mistakes. So, you know, the naive way of creating a queue would be to say, okay, I'm going to just make this my front, and I'm just going to insert some things in there. So like, when I say NQ, I'm just going to use numbers for now. Say I NQ at 2, and then this shifts over by 1. This, of course, F is just an integer in this case that represents the index that's next available. You could also make it a pointer and then use like pointer arithmetic, but nobody likes that. Plus, it's weird. So yeah, so you can say 2, 5, and then let's say you insert a 1, and so on, right? And then F keeps pointing to the last item you inserted. Although technically here, better term for this would be the B, because it's the back of the Q, right? And then the front is here. And then, you know, suppose you insert 2 more numbers. So let's say you insert a 5, another 5. And so the back is here now. And by moving it, I'm saying that B is literally just containing the index. So 0, 1, 2, 3, 4, 5, 6. So right now it contains a 4, and the front contains a 0. Okay? So suppose that now I want to DQ something. So what would happen is I DQ the 2, and then I have to move up the F to be 1 now, right? So that it keeps pointing there. Cool. Everything is working fine. And then, you know, let's say that we insert 2 more things. So 1 and 2. And now back is pointing to what is going to be the last spot that is available here. And then here comes the issue. Suppose, you know, I want to DQ one more thing now. So this moves over by 1. I'm just going to put the S, but you know what I'm saying. It's pointing to the one above it. And then, you know, and by the way, deleting it is not as trivial as that, because again, when you delete something, you know, here I'm just erasing it, but in the computer, that's kind of not really what you do, right? Because like, how do you mark something as deleted? Like you need to either like use a specific value, or you need to add an X, you know, make this an object that has an extra, like 2 variables, the data variable, and then some flag, like a Boolean flag that marks something as deleted, right? So you got to do that in the first place. Or actually, technically speaking, the way you're doing this, as long as you remember that where the front is, then you can ignore that, right? So yeah, you can do that too. But anyways, the point is that suppose I want to insert one more thing. If I want to insert one more thing, first of all, if I just have no code to check boundaries, I'm going to insert here, and that might work, or I might also sec float. You know, it's out of bounds, so it's undefined behavior. So depending on your OS, you know, this might or may not work. Either way, it's bad. So the other alternative to doing this bad thing is, of course, to resize, right? So you have to resize, and when you resize, you know, what you do is you copy all the way from F to B. So you would copy like 1, 5, 5, 1, 2. And then let's say you resize like an extra few spots, and then you can keep going, right? So, you know, let's say that we insert a bunch of other numbers in here. I'm just going to call X or whatever. It doesn't matter what those numbers are. And then eventually we fill it up again. But then we DQ maybe 3 things. But then we want to insert something else. And again, we run into the same issue. We have to resize. But here's the catch. We keep resizing, but we have available spots that like aren't really holding data, right? And that's exactly what I want to get to. I'm very glad you said that, because that's what I wanted. Like, yes, you guys should think about like, well, yeah, but couldn't we wrap around? And yes, that is the right answer. You do want to wrap around. That's the good way of doing it, because then you actually can maximize the usage of this. Now, of course, even if you wrap around, if you fill it up completely, then you do have to resize. But the point is that when you resize, it's because you actually need to resize, not because you bad coding that you left like half the thing empty, right? So yes, the right way of doing the queue is doing what is known as a circular queue. And yes, the concept is as simple as that. You just wrap around. So how do you do that easily? Well, you know, you just have to remember, this requires a little bit of like math, but like very basic math. So for example, when you run out of space in this one above here, so let's say that we're in this situation here and we want to insert something, you know, the indices are going from 0 to 6, right? So what is the size of this? The size of this is 7. So let's just say S is equal to 7. So 2, 4, 6, 7, yeah. And so we can do an if statement and say if the next index where we're going to insert is equal to the size, or greater, you know, or greater than the last number of the index, but equal to the size is easier to think about, then go ahead and just set that to 0 and then keep going. That's one way of doing it. Another way of doing it, which is pretty ingenious, is to use modulus. I didn't know that till like some time ago. Somebody like I saw some code, somebody do that. I was like, oh yeah, you can use modulus for that. Because modulus will, if you want to insert at like 7, well, 7 mod 7 is going to just be 0, right? Because there's no remainder. So that would go here. Now, you always want to check to make sure that the number you're inserting at is going to be behind f, okay? So if you ever are inserting, so there's two ways to track this. You can either have your b and your f point f pointing to the first valid number and b pointing to the last valid number. If you do it that way, then when you increase this by 1, even if it goes around, you know that that's an okay place to insert. Same with here. But the moment that these two are equal to each other, it's one of two cases. One of them is you're overriding something, in which case you should not do that, resize. Or the other scenario you might run into that is if you are emptying things. So let's say that we empty this whole thing. Okay? So as you're emptying it, we'll actually leave those numbers in there. As you're emptying it here, when you're about to empty the last value, or when there's only one item in your queue, which is both the front and the back, that is another scenario where the f and b are equal to. But in that case, because the f is the one that's moving to where the b is, that's a valid number. It's just saying that it's one valid number that's there. So if f and b are pointing to the same spot, but you got there because you moved the f, then that's okay. It just means the queue has one element in it. On the other hand, if the b is the one that hits the f, that means that you are running out of space and you need to resize at that exact moment. Not that you resize later, but like right there and then. Okay? So those are the two special cases that you have to do. So to save time, I actually have some code from last semester that I wrote live, but this time around, there is no reason to write it live when I can just copy paste it. Plus, it's actually somewhat not neat handwriting, so yeah. So here I have an example. There we go. I am doing this circular queue as a circle because it's a little bit easier to visualize how the wraparound works really smoothly. In this case, I don't know if I did the B and F thing, as I said, because the other way that you might see it is where like the B points to the next available slot. That can work too. And yeah, so let's see. So we got T, M, F, O, N, S, A, A. Or technically we start at the A. Actually, no, because the B and the F are pointing to the same thing. So that means that it's full. But yeah, so here's an example of inserting. To insert, I increase the value of B by 1 to see what the next index is going to be. And if that number is equal to the size, I put greater than or equal to because it's like being paranoid when you're coding, this should hit when it's equal to, but if like you have some weird bug somewhere that like increase B extra or something, I want to be able to catch that. So that's why I put greater than or equal to, but technically equal to is fine. Okay? It's just like, it's better safe than sorry kind of thing. So yeah, in my case, I just set that to be equal to -1 because then I have this little line of code that increases the size of B by 1, and that's where it inserts, right? I'm using pre-increment so that it does it in one go. But because I wanted to make this code fancy like this, that's why it's set up like this, where I set it to be equal to -1 here. I could have also just put an else statement where I would do this, but then here in the if statement, I could actually do AR_B or AR0 equal to C or something, okay? That's the way you would do it, the way that I did it traditionally, actually. But then I discovered this modulus way, which is pretty cool. As you can see, it's a one-liner, so that's always cool. In which case, I'm doing the increase, but I'm also modding it by size. And again, that is a pretty cool way of doing it with a single line. However, as I have these, neither of them are actually checking whether we are hitting the F or not. So you would have to add that check at some point in here. So that check should be something like if B is after you do the increase, or right before. Actually, technically, I would do the check right here. And I would do the check and see if b is equal to f, and if that is, then resize, like call your resize function right there or here. You would do that. Okay. Actually, let's write it in. Why not? So, I would say if b plus 1 is equal to f, and I'll go ahead and call it resize. So suppose that's your third operation in the queue, but only in the array version. Is you have your enqueue, dequeue, and then you have your resize. Okay. And then, of course, you got to make sure that after you resize, that you set b to whatever value you want it to be -1, so that the plus here doesn't break your code and whatnot. But yeah, okay. And you would want to do the same thing where you see the red marker there, same way. For the dequeue, that's pretty easy too. All you got to do is basically remove whatever you want. Depending on, again, if your f is pointing to the item you want or if it's pointing to the item next to it. In my case here, I guess I was pointing to the spot before it. That's why you see the plus f. So I have to flip that to f plus in my case if I actually made f point to the element that is actually going to get dequeued. But yes, same thing. And then the modulus again to do the wraparound correctly. Okay. So yeah, that's actually all there's to that. Let's see if y'all understand it. So maybe let's do a quick example of it by just taking. Let's take this one and just do that. So let's clean it up. And I guess when it's empty, you gotta decide what f is going to be pointing to, right? Is it going to be pointing to the next available spot or like what, So, let's just say it's just pointing to -1 or something, because that way when you insert it and you increment the f by 1, then it becomes 0 or something. Okay. So let's say that we insert some value. Again, it doesn't matter what we're inserting. So now f is pointing there. So what is b pointing to? Well, b is pointing to the same thing because we only have one item there, right? So then we go ahead and we insert something else. So then we can go ahead and move that there. And then let's insert something else. So that gets moved there. Let's remove something. So if we remove something, we can move this here. And let's insert like 3 things at once. So like 1, 2, 3. So the b goes here. Then let's remove like 1 thing. Move that there. Let's insert 3 more things. 1, 2, 3. Goes here. And let's insert 1 more thing. It goes here. And as you can see, we are already all wrapping around because we're back to 1, right? And then if we want to insert 1 more thing, that's when we're like, okay, those 2 are equal to, so we need to handle that. And how do we handle it? Resize. What to resize to? You can double the size each time. You can also do a fixed size that you resize. Just be careful though, when you resize here, you can't just copy things directly. And in the naive method here, yes you can, because it never wraps around. But because in this method things are wrapping around, you can't just go and say, okay, duplicate, do like a deep copy of this array by just looping through it. You can't do that. Doing that is going to cost you a lot of problems. What you need to do is you just have to dequeue everything at once, or write a function that starts copying from wherever like f is, and then copies all the way to the b, including the wraparound if required, which actually will be required because you're resizing more than likely because, well, the one case where you wouldn't be required, I suppose, is if you never wrapped around and you just filled it up in one go. Then you're okay. But most of the time there probably will be some form of wraparound. Because, I mean, what are the odds you're just filling in, I guess? You're probably taking things in and out, right? But, yeah, so that's another thing to keep in mind. So, the easiest way to do this is just to allocate your new queue and then just call create a loop that just calls the dequeue function, just one at a time. And just as you call DQ on one, you call NQ on the other one. So, and like literally, if you write the code correctly, you could probably do something like this. Let's say EQ is for NQ, and in that you're gonna put like DQ of the other one. So something like that, you know, and then you just like loop that basically nonstop until you're done DQing. So yeah, I don't know if you actually get to implement a circular queue this semester. I do have an assignment for that, but I believe I have that disabled just because it was one too many assignments. It was called queueception, because I had queues inside of queues, which is pretty cool. Basically kind of making it, and by the way, queues like this are very useful for scheduling processes in a computer, and you will definitely revisit this kind of stuff when you get to 370. So CS 370. So it's not going to be the last time that you see these. Okay. So, yep. Any questions on queues in general? I don't know if I went a little too quickly, but again, the stuff is still just using arrays and linked lists, which is pretty basic stuff, right? How do you differentiate B hitting F versus F hitting B? Because that's a good question. When you are running your code, you will only be hitting, so F hitting B is only going to happen in your DQ function. B hitting F is only going to happen in your NQ function, right? So because you know that, then you can work with those in those specific functions. So you're only ever going to have to resize in the NQ function. And the NQ function is the one that's going to be hitting B hitting F. And so that's how you handle that basically, okay? And your DQ is the one where they hit. In fact, you know, the only thing you gotta the only thing you should know is that when you're DQing, you know, so you don't segfault because you're like DQing something empty, or so you don't like print out invalid data. That's your stop basically. Like you have an if statement at the top that says like, you know, if F is equal to B, then like return the function or print out to the user like the queue is already empty kind of thing. And by the way, that's a good point that I want to bring up that I don't think I said with the stack. So with the stack, you know, what happens when you try to pop from an empty stack? Well, that's up to you. You could crash the program and say like, you know, invalid data, trying to pop from like -1 or something. But you could also just say again, if the stack is empty, how do you remember the stack is empty? With an array, you can just see, you know, if you're trying to pop from a negative value of an array, that's obvious. For the stack, of course, if you have it empty, then you're going to see a null pointer, so you can just be like null pointer section. No, you can just say like, okay, this is empty. With a queue, again, with a linked list version, you can just use the null pointers and say this is empty. But with the circular array, then you just check if F is hitting B. Okay, so yep, that's all good information. And by the way, you will hear the term top also being referred to in queues. That is usually the same thing as the front. And in both stacks and queues, one other term you might hear is the term peak as a function. And usually has some sort of parameter. What that is a function to sort of peek or to take a look into your stack or queue at a specific index. So if you're trying to look at the 5th element in a queue, like the 5th next element to be printed, like who's behind the, you know, like if it was a second, it'd be like who's behind the front. Then you can use peek for that and pass in like a number there, an index. With a stack, it's counting from the top to the bottom. So peek 2 would be the one, you know, again behind the top of it. Again, peek is the function that like with the linked list is inefficient, but with an array is very efficient. And that's the one pro of implementing an array stack. With the circular, by the way, with the circular array, let's do the same little table that we did before. So queue. So we have, I guess technically we have 3 ways. We have, here, let me make that more central. We have the array version, we have the circular array, And then we have the linked list. Okay? And we have our insertion, which we'll call NQ. And then again, your retrieval / deletion are combined into one function called DQ. But let's throw in this peek function in here as well. Okay? So for this, for the NQ, for the array, the normal array version is going to be O of 1, but there's an asterisk involved because that can become O of n if you have to resize, right? So I'll do a little extra thing here called resize if resize required. Because if resize is required, then that becomes O of n. And it's important to specify these kind of things. So when somebody asks you the time complexity of an operation, and you'll see that in the worksheet, it's not just about giving an answer with a number. It's about explaining your answer to make sure that there's no assumptions taken by mistake. If you take an assumption to answer a question on a test, make sure you state that assumption so that I'm aware of that. I'm like, oh, okay, you were talking about this. Because otherwise, there can be more than one answer for something. And there can also be, something that might be correct in one context is not correct in another one. So those assumptions allow us to clarify that. So, such as this being the case, you could argue this is O of 1, you could also argue this is O of n, depending on the assumption about resize, which of course is kind of a given with an array, but definitely not with a linked list. With a circular array, we have O of 1, which is also O of n, but better, right? It's better because it takes advantage more of the space. And then this is always going to be O of 1. There's never any issues with that. I mean, as long as you code it correctly. And that's the other thing, right? Like, if you code the linked list the wrong way, that becomes O of n. But again, we're talking about coding a linked list that in the way that I showed you. And that is typically when you think about an algorithm, and you give it the time complexity of it, that's assuming that you code it correctly, right? And you don't have a bug in it. Because otherwise, your time complexity could be infinity if you have an accidental loop that just loops infinitely there, right? So if we're making that assumption, that one is, you don't need to state that. That one is obvious that you're giving me the time complexity of code that is correct. Yes. Okay. So yeah, for the DQ, that one is going to be O of 1 regardless. There's never a scenario where that wouldn't be O of 1 if you code things correctly in both of these methods, and of course in the linked list. And for the peak, this is going to definitely be O of n because you have to traverse the linked list in the worst case scenario. But for the array and the circular array, that actually is O of 1, which is pretty neat. It's just a math operation you gotta do, which is a constant time. And then there's no resize, not applicable, I suppose, for linked list right there. Let me scroll up. Okay. All right. Now I think we're fully done with the queues, unless more questions come up. But yeah. Okay. If you have any questions, go ahead and throw them in right now. Otherwise, I will start with sorting for the last 20 minutes of class, because we can probably get some of the basic sorts done. Technically speaking, the sorting we're going to talk about is comparison-based sorting. There's different kinds of sorting, but comparison-based is the traditional way. Most of you probably learned bubble sort at some point before this class, whether that was in 202 or just on the internet. It works, and it's reliable, but it's not quite fast. It's easy to code, really fast to code. 2 lines, 3 lines of code, 3 or 4 lines, because you have 4 loops and 2 statements in the loop. But of course, nobody would ever use bubble sort in a serious scenario. So yeah, let me pull out my notes on all the sorts that we're going to do. I think I have some preface stuff that I want to talk about before sorting. So at the end of this, we are going to make a list of time complexities. It's going to look like that. Of course, there's also the internet where you can find a list that already has most of the sorts in there, and there's a really good reference sheet, definitely useful for the test. By the way, the test is open notes, so you definitely want to make things easily accessible, because the strategy is you get a lot of questions in a short period of time, because we don't want you to be looking up every single question. We want to make sure that you know the material. However, we expect that some of the questions you might be like, I don't remember this bit. So, you want to have the knowledge there, but still, if something is not clicking, you can quickly reference it. But if you have to read and reread something entirely, or rewatch a piece of the lecture, or remember something, that's when you're like, oof, you run out of time. So definitely make a cheat sheet and that kind of thing, and definitely have this big chart when we finish sorting ready to go in case I ask something from it. Bogus sort, yeah, I will talk about bogus sort a little bit actually, and the memes and whatnot. But if you go on Canvas, by the way, I can share my screen. I have some resources for that I want to show you. By the way, big O links. They're the big O links, I guess. Big O cheat sheet. It's really cool because you can see the time complexities. Obviously, again, this stuff is tricky sometimes, but when something grows quicker, what we're saying is that the program gets slower faster because the time it takes is growing, meaning there's a lot more time the program takes to run. So faster growth rate means more time a program takes, which for us means slower running program, okay? So when you see things going up, that means they're going slower. So this is Big O cheat sheets, and again, the link was here on the week 2. If you scroll down, I think that's pretty much an identical of what I have in that piece of paper here. So definitely print that out, or save it to favorites toolbar or something, or screenshot it or something, so that you can reference that. Okay. This also, by the way, here, let's look at how they listed the array and the stack. See if they said for stack the time complexity of access takes O of n. The reason why they're saying it like that is probably because they're saying how long it takes to print out the entire stack. So if I wanted to just print out the entire stack, of course it's taking O of n time because they got to access every single element. But really, when you're seeing here, and searching the same thing, there's no fast way to search that because it's not sorted, so you can't use binary search. That's why. Oh, by the way, I know this is really tiny. Let me enhance it. So there we go. Yeah, so that's why this thing says O of n here, and under the search and access, insertion deletion is that. But what I said is still correct in the sense that when you're trying to remove something from it, like a DQ or a pop, it's still going to be O of 1. Okay. The space complexity is interesting, but as you can see, for most of these algorithms that we're doing is O of n. That's why we don't really talk about it. But yes, all of these, there's no magic. You can't do like a black hole where you insert 10 numbers and it only takes 5 space for 5. So there's that. Anyways, that's a good reference. So definitely check it out. And then I think that's the only reference that I wanted to know. Oh, no, actually, quantum storage. With the quantum stuff is interesting, but it's a little bit overhyped, unfortunately. Yeah. Sad. But anyways, I have also references for stacks and queues that link you to a bunch of things from Geeks for Geeks, which is great. I guess there's the book too. And also from some of the sort algorithms, okay? And then this is the one that I wanted to actually reference. This stuff, quicksort, we'll go far away from that a little bit. This here. Okay, so let's just take this in slowly. I believe this is from this webpage here that you can check out. But let's kind of understand what this is for a minute. So a lot of the times when you're thinking about sorting, you think that, okay, the fastest sorting algorithm takes this amount of time, this amount of operations, and if we analyze the asymptotic complexity of the best sorting algorithms, you'll find out that they take n log n time. Okay? So you might be saying to yourself, can I do better than that? Don't let your memes be dreams kind of thing. So can I make an algorithm that can sort faster than that? And there's been a lot of attempts at doing things like parallel programming to sort faster. And yes, you definitely can sort faster with parallel programming, but I'm strictly talking about something sequential. What's the limitation? How fast can we do it? Is there some amazing way that we can sort faster than n log n? And it turns out that the answer is, they always say don't give up on your dreams kind of thing. But I'm sorry to tell you that unless we do invent some sort of time travel and whatnot, that we are indeed limited to a n log n speed. Okay? So there's no way we can make an algorithm that can complete something in n time, linear time, like a sorting algorithm. And this is not just, half sorting, but I'm saying if you give it some data and that data is completely random every single time, we're looking and seeing what that lower bound of comparison-based sorting is, and it's still going to be n log n. There might be bubble sort can achieve faster than n log n if you feed it a specific order of the data, in which case is a sorted list. If you feed it a sorted list, bubble sort runs one time. If you put an if statement that says there's no swaps in that iteration, it should break out of the for loop and return. If you do that, then bubble sort it takes n time in that scenario. That's going to be your omega of n. And you're like, oh snap, that's faster than the n log n. Yes, but that's with specific data. I'm saying if I feed it all possible combinations of numbers in the universe, which is a huge amount, infinite, I guess, but if you feed it all of those, there will never be a scenario where if I feed it all possible combinations to a magic algorithm, that it will be always faster than n log n. That can never happen. Okay, that's what I'm saying. So if I have this magical, let's say that this box is like a magical sorting algorithm. Okay, if I feed it some numbers in here, sometimes it takes n time, sometimes it takes n log n time, sometimes it takes n squared time. If that's the case, then this is n squared. This is bubble sort actually. Okay. If I have another algorithm like quicksort or merge sort, actually quicksort is not that good, but merge sort. If I have merge sort in here, merge sort takes n log n time regardless of the numbers you feed it. I cannot find a combination of numbers in the universe that can make merge sort take more time than n log n. That's good, because then that's my limitation. That's like saying, okay, this merge sort right here can do things whether it doesn't matter what, even if I handpick the numbers to be really, really bad for merge sort, I can never make it take longer than n log n. That's what we define as our big O. That's the bound that we care about. Quicksort, the reason why I say it's not good is because there is a scenario in quicksort. It's very rare that you can actually make it take n squared time, which is not. It's literally the same speed as bubble sort, but it barely happens. It's like winning the lottery, except. Maybe it's actually better would be it's like getting hit by lightning. Okay, yeah, it can happen to us and we can die, but it's so rare that you don't walk with fear. Well, unless it's like a massive thunderstorm and there's lightning falling around you, then I guess the odds are a little higher and you should be afraid, I guess. But yeah, you get what I'm saying. It's so unlikely that we don't care too much about it. But still, technically speaking, asymptotic complexity wise, it's n squared. So n log n is really good. But can we do better than that? Answer is no. So, why am I so resoundingly saying that the answer is no? Why? Is it just because I am my mind is limited to this world? Well, no. It's because the mathematician people have actually proved that you can't achieve comparison-based sorting faster than n log n. And that's what this proof is. So I welcome you to click on this link and look at it in detail to understand it. And obviously, they'll probably go more in depth in analysis of algorithms class. But for now, I'll give you a quick introduction onto how it works. The math looks nice when you see this. It's there's no fancy stuff. Whenever you see a proof of something, you see integrals and derivatives and differential equations and transforms, and you're you're just yeah, no, I'm gonna go home now. But here, it's pretty straightforward. There's some exponents and logs, and that's it. So let's kind of just go through this. And again, that's from this source. I did not come up with this. And they didn't come up with it technically. Whoever solved this, you know, it's big. So yeah. Okay. That's a good question though. I don't know when they figure this out, but it probably didn't take them that long based on the math. But yeah. So considering the problem to sort n distinct numbers, so we have distinct number of numbers, I guess. Any sorting algorithm must be able to distinguish between the n factorial permutations. So let's stop right there. What do I mean by n factorial? Remember what n factorial means is like 5 times, so 5 factorial is the same thing as 5 times 4 times 3 times 2 times 1. So when you take discrete mathematics, I think the second one or the first one, I think it's the second one, they're going to talk to you about combinatorics, like combinations and permutations. So they'll explain what they mean by permutations. But for now, just trust me when I say that if I want to find out in how many ways I can combine 5 numbers, then the way I do that is I just do the factorial for that. So if I say I have 5 numbers, and then we figure out in how many ways I can organize those numbers to be different. So like what I'm trying to say with this, I want to make sure we're all on the same page, because I know when math comes into the topic, people get scared. So if I have 5 numbers, so I have 5, 4, 1, 8, and they're distinct numbers. Again, if they're not distinct, then you got to use combinatorics, and like there's formulas for this, and yeah, even I don't remember them very well. I would have to like refresh my mind and go on Google. It's like NCE or something. Yeah. But anyways, the point is I have these 4 and 5 numbers, right? I could also organize them like this. I could also organize them. In fact, here, let's just take 2 numbers. How many ways can I organize those numbers? Well, I can just do 0, 0 or 1, 0, and that's kind of it. If I have 3 numbers, this, you know, I can do a lot more. I can do 1, 3, 2, 1, 2, 3. Oh my God, I'm not creative at all. Okay, the 1 can go here, and then I can do 2, 3, 3, 2, 1. Okay, so I need one more with a 3 at the end. So I can do 2, 1, 3. Okay, I think those are all of the different combinations that I can do. I think. And this is 2, 4, 6, right? There's 3 numbers. What is 3 factorial equal to? 3 times 2 times 1, which is equal to 6. So, voila. Proof by example, which is not legit, but for now, we'll take it. So, you can see that with the 5s, it would be 5 factorial, so that would be 5 times 4 times 3 times 2 times 1. That is 5 times 4 is 20, times 3 is 60, times 2 is 120. So there's 120 combinations. Like, OMG. Like, think about that. From 3 to 5, and now I go from like 6 to 120. That's hardcore. But that's just that's the way it works. And so, you know, that's a lot of combinations. So what we're saying is, you know, taking what that means, not combination, permutations, like, telling what that means, you know, I'm saying that if I feed it for an n number of these permutations, for these n numbers, you know, I have to treat each one differently to sort it, right? Like my algorithm is going to take all of those different 120 different permutations and is going to try to sort them, right? And if I feed it all 120 of them, you know, and I'm analyzing the time complexity on that, you know, I'm trying to take the one that like it has to understand that they're all different so that it can sort them correctly. And it also we're trying to see how long that would take. And then the slowest of all of them is the one that we're interested in, not the fastest one. The fastest one's probably just the 1, 2, 3, 4, 5 or whatever. Okay, so for the algorithm to decide whether to swap something or whether something is sorted or not is a comparison. You know, it's looking at 2 numbers and comparing them. It's trying to see whether they're in the right spot or if they're not in the right spot. And if they're not in the right spot, it might have a process of how to get them into the right spot. That's called decisions. That's the second line here. The number of yes or no decisions, the number of bits necessary to distinguish between the n factorial permutations is log base 2 of n factorial. Okay? If you think back to like the log rules that I showed you, this makes sense. So remember, when we say log 2 of 8, we're saying 2 to what power is equal to 8, right? So here we're saying 2 to what power, or actually we're saying technically, yeah, 2 to, if we say log 2 of 8, that's equal to 3, right? So what that means is log to what power is equal to 8. So here we're saying 2 to what power is equal to n factorial, okay? Oh, sorry. Here we go. So what we're saying is we have the log 2 of, when we say log 2 of 8 or log of 8 with the base 2, we're saying 2 to what power is equal to 8, which is just a 3, right? So this becomes 2 to the 3 is equal to 8. Here, when we say log of n factorial, we're saying 2 to what power is equal to n factorial. Like that's got to be some big power number right there. It's power play, okay? So the reason why is because for each of those comparisons that you have to make in a computer, binary computer, yes or no, 0, 1, it's an exponent of 2, right? Right? If we have 2 to the third power, that's 3 bits. That's 0, 0, 1. And that can store up to technically 8 combinations, right? 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay? I mean, I hope I didn't skip any. So you can see that that can store 9 decisions. If we're trying to store 5 factorial, we need 120. So in that case, we would need 2 to the, let's see, would be 16, 5, so about 7. I think 2 to the 7 will cover us with 128. So yeah, we need about 7 bits to be able to store all of those decisions, okay? So if we don't know what that's because I'm plugging in a number, but if we don't know that number, then it becomes this log base of log 2 of n factorial, okay? So that's how we get that, all right? Trust me on this. So this lower bound is known as the information theoretic lower bound, okay? So from here is where it's kind of like mumbled through the rest of this. It is easy to see that we have n factorial, which is greater than or less than n divided by 2 to the power of n divided by 2. Therefore, log of n factorial, which again is the number of bits we need, has to be greater than or equal to log of n to the n divided by 2 to the n divided by 2, okay? Now remember that when you have an exponent in logs, you can take that out. So we just take it down here, so that's how you get this. And then of course, these are just constants. It's divided by 2 and divided by 2 are constants. So they don't really matter. So that's how we get the n log n, okay? Now, how we achieve this here, this n divided by 2 and divided by 2 kind of thing, it's a little bit of hand waving, but if you read the rest and you could go there, they can explain a little better. But hopefully you can see that this n factorial, that this log of n factorial, which is what we're looking for, is a number of the number of bits we need. And if that number is equal to n divided by 2 times log of n divided by 2, then that means that this number is a subset of this, okay? Or it's an element of, not subset of, it's an element of that time complexity. Meaning that you can't go faster than that. You can go slower than it, but you can't go faster than it, okay? So it's not quite mathematical what I explained to you, but I think it's enough. I'm just trying to prove a point, okay? Read it definitely. Obviously, you don't know heap sort and mesh sort yet. You will, and we will go into detail of those. But also read about the other kind of sorts like bucket sort and vertex sort. So definitely just check this out. Again, it is on Canvas. Read it, and then I will definitely ask you in the test what the lower bound of comparison-based sorting is, and you definitely know what the answer is, which is that. I'm not going to ask you to prove it because I'm not going to ask you to do something I couldn't do live right now. But you should definitely know it, because it's pointless to try to spend your life work trying to achieve something faster than this when mathematically it's been proven impossible. But like I said, not all hope is lost. This is strictly talking in a sequential manner. It turns out that some algorithms are easy to parallelize, and when you parallelize, you're distributing the workload amongst different workers, which means that you can actually achieve faster, and you can definitely do something faster than this. But that's only because you're parallelizing something. So there are ways around sorting quicker than this, but you're not technically. You're just finding a workaround the problem. You're not speeding it up, truly. Okay? It's like I can only cut paper so fast, but if I have somebody to help me, then I'll definitely cut faster than what my personal limit is, because two people, can cut faster than one. But then again, have I really sped up the solution? Yeah, I got the result quicker, but I'm not able to cut paper faster. Okay, I have no idea where the cutting of paper came from. So that's it. I'm actually glad that we got as far as we did. So that's it for today. Next class, we are going to jump in now into what is actually relevant to this course, which is learning all the sorting algorithms. So we're going to do bubble sort, selection sort, insertion sort, merge sort, and maybe quick sort if we have enough time. If not, we will jump into the next time. All right? So until Wednesday, I'll see you guys later. Don't forget your assignments. And if you have any questions, let me know on Discord. Thanks all for watching, and I'll see you guys next time.